Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I have too many slides here, but it's actually okay if I get through only half of this talk. Some of this stuff you know. Why replication is to make services be up all the time, and the problems that we have to deal with is we want to make the replication consistent, and we want to the various replicas have to be diverse in order for them to fail independently. So if you have a replicated bank, say, if you have deposited some money into the bank, you want to be able to withdraw it later, and for that you need the replicas to be consistent with one another. In particular, we're going to show a technique that will give us linearizable semantics on the replicated object, or in other words, that object will basically behave as if it's not replicated. And for diversity, we need the replicas to fail independently, because if they all suffer from the same vulnerability, then they may all crash at the same time, and we don't have availability. Okay, so assumptions that we're going to make. We talked about this. First, what assumptions are we making about machine failures? So when I talked about on the first 2 days, I assumed a model a fail-stop model. That's a model in which machines can stop, but we can accurately detect when they have. So it has accurate failure detection. And then when Miguel talked about Paxos, he made an assumption of crash failures. And those are also stopping failures. But he didn't make the assumption that they could be detected accurately. And so it's a larger class of failures than fail-stop. And then when he talked about Byzantine, the practical Byzantine fault tolerance, and then basically you make no assumptions about failures. And that's the largest class of failures you can make. Today we're going to use Byzantine, the Byzantine class. I'm going to make no assumptions about failures. And we also talked about various assumptions one can make about timing. We could make a synchronous assumption. I was told not to move around too much. Cameraman, I tend to move a lot, so I'm not going to do that today. So the strongest assumption we can make is synchrony. There are hard bounds on computational steps, hard bounds on network latencies. You can weaken that to semi-synchronous, which I usually define to mean that there exists a bound, but we don't know what it is. And then, of course, the largest class actually, it's no assumptions whatsoever. The weakest of all assumptions, that it includes everything, is asynchrony, where we make no assumptions whatsoever. And again, less is more. The fewer assumptions we make, the more robust our system will be. So, Byzantine, asynchrony. What we are going to assume is that most F processes can fail. So there is an assumption that we have to make, bound on the number of failures. Asynchrony, no assumption on times, and we do assume that correct processes that don't fail, can communicate somehow. So if they send a message to one another, eventually that message will arrive. That's the assumptions that we're going to make. And then, of course, you're already starting to dread this thing. Oh no, not another one of these complicated Byzantine whatever talks that are very complicated, very hard to implement, and besides, these Byzantine failures, do they actually happen? And they're extremely expensive to run, and what kind of an assumption is that in any case? We heard end version programming doesn't really work. Failures are dependent. And do we really need it? Like so I was going to be talking about the cloud. Cloud data centers have all this security built around them. So let me try and argue that in fact Byzantine failures do happen. Again, an Amazon example, a different one. In 2011, last year, the elastic block storage went down due to a so-called Mendel bug. A Mendel bug is a bug that's very hard to reproduce. 2009, a few years before that, the Google file system had a similar problem. Again, a Mendel bug, usually caused by concurrency, as it turns out, that caused an outage. In fact, there is this paper from 2007 before that between 15 and 80% of all software faults are caused by Mendel bugs after release, or are detected after release. So that's a fairly large range. I have some better stats. So here's a stat of disks, SATA disks. Like 8.5% of disks, SATA disks, these very common disks, develop what are called silent data errors during their lifetime. Like they will, when you read from the disk, they will provide data, and they will just say, here's no error. The checksum went through somehow. I don't know what happened, but in any case, they give you the wrong data. In databases, this is a study from 2007. Actually, there were two different studies in 2007 of various commercial databases, and it found that more than half of the failures were not crash failures, but Byzantine failures of various kinds. Incorrect answers, the database getting corrupted, unauthorized access. And of course, in a cloud, and you've got many of these databases and many of these machines, these kinds of Byzantine failures happen all the time. So yes, so that's here's another study of BGP, the Border Gateway Protocol. Apparently, those have all kinds of interesting failures. And what the study has shown is that, again, it's of the Mendel bug variety. The bugs, if you replay the input to these servers, they don't necessarily crash each time, but only once in a while. And different versions have different bugs. And so that's good news and bad news. Like the good news about all that is that that these failures seem to happen fairly independently. They are pretty non-deterministic. And the bad news, of course, is that they happen at all. So, as Miguel pointed out, even though clearly these Byzantine failures do happen, nobody has deployed them. And part of that is the complexity. I mean, companies don't like to deploy very complex code. And it's also very expensive, right? We talked about 3 F+1 replicas to tolerate F failures. That's a lot of replicas. And a lot of messages flying around, all these old-to-old communication steps. It's very expensive. And then crypto, many CPU cycles. Well, companies like to use their CPUs for other things rather than signing and decrypting messages. So those are some of the reasons, I think. And then the question is, well, can we do better than that? Well, there are various lower bound results, like from 1983, shows that, if you want to tolerate Byzantine failures, you need at least 3 F+1 replicas. Can get around that, unless you make some more assumptions. And so today we'll see, like maybe by making some weak additional assumptions, we can do a little better. Okay, so I'm going to try and be fairly precise today, rather than before where I sort of gave fairly informal types of specifications. So here's the specification of an object. It has a history, and the history is a collection, a set of pairs of a sequence number or slot number and a command. So the slot numbers are number 1, 2, 3, 4. And for example, in the case of the bank, you might have that in slot 1, there's a deposit, $500 operation into some account. And slot 2 may have the withdraw $100 operation. So the bank can maintain a history of all the operations that happen to it and in what order. And from that history, we can derive, how much money is in the account. I find it personally easier to think about state as a history of operation rather than the running state. It's much easier to look at what the consistency properties are of a system by looking at a history of its operations rather than at whatever its current state is. So I'm just going to work with histories, and we can derive a state from it just by executing all these operations against like a bank account in this case. And then besides a state, a system has transitions. And so what a transition is that you apply something to the state, which in this case adding something to the history. So the specification of an object in this case is one transition. We're going to be able to apply an upper or command C to a slot S. And what that means is we're just going to add that pair to the history. The history becomes, add that particular pair to it. But you're only allowed to do that if there's not already something in the history for that particular slot number. You can only add one command to the slot number. That's what is going to give us our consistency. So this is a very abstract, high-level specification of anything, right? It could be a bank, it could be any kind of object. History is a set of commands, and doesn't, so the only way that you need to add in order to talk about a specific kind of object is to talk about what operations are possible on the object. Okay, so that's the specification. And there's some important observations, invariants, that one can make about this specification. Once a particular operation is in the history, there's no transition that takes it out. There's only add something to the history. And that means that operations have to be persistent, or in database terminology, durable. Right? Once it's there, it stays there. And also, again, from this particular specification, we can see that it's not possible to have two different commands in the same slot number. And that's the consistency part. One thing that's a little funny about this specification is that we're not specifying in what order slots have to be filled. You can put something in slot 2 before you put something in slot 1. There's nothing that says that you have to put something in slot 1 before slot 2. And why is that? Well, I mean, there's no particularly good reason for it. We can certainly strengthen the specification. But if you do that, you limit the number of implementations that you can make of this particular specification. And as we saw in Paxos actually doesn't fill sequence numbers or slot in a particular order. The different slots can be decided in parallel. And that means that slot 2 can be decided before slot 1. So I didn't want to make that restriction, and there I haven't. It also keeps the specification simpler. Right? If I had added this kind of, fill slot 1 before slot 2, it makes the specification harder, and it makes, therefore, also the implementation harder. Okay, so how does one implement a specification? Well, you use something called refinement. You make design decisions. You have to figure out how am I going to implement the state and how am I going to implement the transitions. The implementation itself is just another specification. Happens to be an executable one. And we can prove whether one specification refines another specification by exhibiting a map of the state of the implementation, or S prime in this case, to the state of the object, in this case a history of operations. And we have to show that any transition in the implementation corresponds to a set or sequence of transitions in the high-level specification. 0 or more, typically we do 0 or 1. So it doesn't have to be every little thing that the implementation doesn't need to correspond to an apply transition in our specification. A lot of it is what are called stutters, just stuff that the implementation does to its state. But occasionally there's a very important transition in the implementation that corresponds to a transition in the specification. Okay, so now we're going to get to what these, we're going to implement this particular specification that we had. And the first thing I'm going to use is introduce something called a chain. And a chain is a configuration, and a configuration is or chain is a list of replicas. So typically before we talked about a set of replicas, but I'm going to use the notion of a list of replicas. So there's a first replica and a last replica. And we're going to assume that at most the minority of those the replicas on the chain can fail, which means you need at least two f+1 replicas. So where f is the number of faults that can happen, because you need a majority, f+1, to be correct. We're not going to require 3 f+1, as it turns out. And that will surprise you at this point, hopefully, because we saw protocols that were supposedly optimal that used 3 f+1 replicas. I'm only going to use 2 f+1, so there is going to be a catch at some point. Okay, I'm going to assume there's an infinite sequence of these chains, of these configurations. Later we're going to change that, but at this point, let's just assume there's a sequence C1, C2, C3, somewhat in the same vein as the views that we saw in virtually synchronous group communication. Okay, replicas. They're going to have, yes, question. So the replicas, well, you'll see later why we need it. But yes, both the chain is ordered, and the list of chains is also ordered. So there's only one of these lists. I think in a minute you'll know why that is. Oh, probably more like 2 or 3 minutes. If I go too fast, slow me down. If I go too slow, speed me up. I'm not going to move too much, don't worry. So the state of a replica has two variables. It has a mode and it has a history. The mode of a replica is one of three. It's in one of three states, basically. It's pending, or active, or immutable. And initially, all the replicas in C1, the first configuration, they're all active, whereas all the other configurations have pending replicas. Now, replicas can also be Byzantine, in which case it doesn't really mean anything what that state is. So mostly this refers to the state of correct replicas. So correct replicas are either pending, active, or immutable, and initially only the replicas in the first configuration are active. And these active replicas, and Byzantine replicas can do whatever they want, create these certificates that are pretty similar to the prepare certificates that we saw yesterday in the Byzantine Paxos version. I'm only going to talk about two different kinds of certificates today that are with which we're going to do ordering and recovery. So it's going to be a little simpler. So an order certificate has a slot number, command number, and it's signed by some replica row. So only active replicas will make these order statements. So and of course Byzantine replicas can do whatever they want. Active replicas will never create two different order statements for the same slot with two different commands in it. But Byzantine replicas can do that. It's probably on some later slide too. Okay, let me talk a little bit about chain replication. This is something Peter was going to talk about too. Something that I designed in 2004 with my colleague Fred Snyder. And it's actually today used in a variety of key value stores. It's a very simple replication scheme, and the 2004 paper didn't talk about Byzantine failures, only about fail-stop failures. But the idea is you have a chain of replicas, in this case 3 replicas. The client sends operations to the first replica on the chain, which is called the head. The head adds that operation to its history, which we'll see more about later. and then forwards the operation to the next replica. Next replica applies the operation, forwards it to the next one, and then finally the operation arrives at the tail. The tail applies the operation and then responds to the client. Very simple replication protocol. Certainly in the absence of Byzantine failures, it's fairly easy to see how it works. So the head assigns slot numbers to commands. This I already said, I think. And then the the way it works in this particular situation is that each of these replicas is going to create an order statement and forwards the order statement to the next replica, and then the next replica adds a new its own order statement, and so we get all the way to the end of this chain. And so at the end we have 3 order statements if there are no Byzantine guys, and the tail sends that entire set back to the client. The client, if it sees order statements from all 3 replicas for a particular slot number, decides that it's decided, that believes the outcome. Now, some of the replicas may be Byzantine. Doesn't matter. All we need is that a majority of these order statements are correct. If the Byzantine replicas add order statements that are consistent with the other ones, we're not going to worry about that. So that's the basic idea of chain replication. And the important property is that any response that a client sees, all the correct replicas have created an order statement for that, and they keep that in their state, so they will remember that. Is that part clear? It's pretty straightforward. I'm not trying to give you any hidden, complicated things here. It's just simply a very simple state. Yes? It might decide not to forward. Yeah, no, it only says if a client receives order statements from all replicas, then the client learns that it's decided. If the client doesn't receive anything, it doesn't mean anything. Yes?
The client receives that Byzantine, the replica that is Byzantine, might have forwarded the message correct, but might not execute what.
Absolutely. So Byzantine.
It doesn't have enough. If the client believes that it's a quorum or a majority.
Right. I mean, the client sees 2 F+1 order statements. It knows that F+1 of them came from correct replicas. It doesn't know which F+1, and so there may be F from incorrect replicas. But it only decides it if all 2 F+1 have the same slot number and the same command in it. So the Byzantine guys have to play along in order for the clients to learn things. But it's true that the Byzantine replicas may, after that, throw all that state on the floor and forget about it, or replace it with something else. There's nothing a Byzantine replica cannot do, except forge signatures on messages from correct members. Cannot do that. Yes?
I guess that was my question. So you rely on signing to...
Yes, all the order statements are signed, and we rely, it's an assumption that I didn't make explicit, but it is definitely there. The one thing a Byzantine guy cannot do is create order statements that are signed by correct replicas. It can certainly create order statements that are signed by other Byzantine replicas, but not by correct replicas. Yes? Sorry, I'm not hearing well. Yes? That's correct. So the comment is that if a Byzantine client doesn't forward anything, the client will not get a response, and the system is down. That's why we have more than one configuration. But in one configuration, that's exactly right. If there's a crashed replica, for example, and crashed replicas, that's a special case of a Byzantine replica, client will not get a response. Okay, so as I said, we need to, in order to show correctness, we need to exhibit a refinement mapping. So the refinement mapping in this case is very simple. The history of the abstract specification is simply the set of slot command pairs for which there exists a configuration so that all replicas in that configuration have issued an order statement. So as soon as there's a order statement from all replicas in the configuration, then that's in the history. That's the entire refinement mapping. Is this clear? A little math sometimes does wonders. So hopefully that is clear. Sometimes it's clearer than waving your hands. So it had better be the case, if this is the refinement mapping, that processes cannot withdraw statements, and correct processes cannot withdraw statements. But in fact, once a Byzantine process gives one of its statements to a correct process, that correct process can hold on to it, and it will always be a statement from that Byzantine process. You cannot withdraw statements. So, by the way, statements here is a very abstract concept. Sorry, I'm moving too much. An abstract concept. It's simply the set of certificates that have been created, not necessarily observed. So it's an abstract variable. But in any case, processes cannot withdraw statements. But a Byzantine process can certainly sign statements that conflict with one another. It can create an order statement for command 1 and an order statement for command 2 in the same slot. And it also has better be the case that there cannot be two different configurations, one in which all replicas have issued an order statement for command 1, and one in which all correct replicas have created an order statement for command 2. Because then the history would have two slot command pairs that conflict with one another, which is not allowed by our abstract specification. By the way, one thing that I didn't say is I do assume that the configurations are disjoint for simplicity of the story. So two different configurations have different sets of replicas. It makes the story a little easier. For the actual implementation, you just need, an incarnation number or something on machines. But think of it as disjoint replicas. So better have these properties. And as we'll see, we'll get these properties. Okay. Talked about the mode. I talked about order statements. I haven't talked yet about the history of a replica. The history is the other variable, right? It has a mode and a history. The history is a set of what I call order proofs. An order proof is one of these tuples. Let's see, how does this work? So it's a slot number, a command, a configuration. Sorry that they're both called C, but that's a command and that's a configuration. And then there's a set of order statements. This is, by the way, the history of replica row. It's a set of order statements such that the replica assigned by replicas that are in the configuration C and and row prime are the predecessors on the chain, right? So chains configurations are ordered chains, and so we want an order statement of all the predecessors of row. Right? So in the case, if it's the head, this could be the anti-set because, it would only include its own order statement. The case of the head of the chain, because there are no predecessors. The case of the tail, it would have to include order statements from all replicas in the chain. But any process in the middle of the chain only needs its own order statement and the ones of its predecessors. Initially, there's no history. Is that clear? Good. Let's see. Note, let me read this. I already said this. If row is the tail of the chain, it has order statements of all the replicas in the chain, and so it has it has a proof that it can send to the client and convince the client that command is durable. Even if that tail process is Byzantine, there's nothing that prevents the tail from throwing away that proof. But if it sends it to the client has no reason not to believe it. Okay, here's the protocol, and I'm not going to, so this is again in math. And again, I'm not going to go over the math in this case. A lot of these quantifiers and other kinds of things. It's something called a state transition specification, and for example, Nancy Lynch's I/O automata are an example of that. I find it personally convenient to talk about these things. So there are the transitions. It's the same as that specification we saw before, but we got 3 transitions here, and for each transition there's a precondition and an action, the thing that updates the state. I'm going to now use English to talk about what these transitions are. So there's 3 transitions that replicas can execute on their state, the mode and the history. The first one is the order command transition. That's where it creates one of these order statements. So when a replica receives from either the head replica, in the case of the head replica, it would be from the client. In the case of other replicas, it will be from the predecessor on the chain. A message, then it creates an order statement and a proof. So the proof is the proof that goes in the history. Wrong button. Order proof, right? One of these things. So it creates an order statement and a proof, which is the set of order statements that it got from its predecessors. But it's only allowed to do that if the replica row is active, and only if all the predecessors, all the order statements that it got from the predecessors are correctly signed. And then there's another thing, and it also looks in its history to see if there's a conflicting order proof. If there's a conflicting order proof, it will not do it. There's another transition. These 2 transitions have to do with recovery. What if something goes wrong? If something goes wrong, a replica can always go from active mode into immutable mode. It says, okay, I'm throwing up my arms. I don't know what to do. I have the feeling that something is wrong, and it may be that the client said, hey, what's happening? I don't get any responses. Well, in that case, the replica goes into immutable mode. And it generates a statement containing its history, signed statement. So once it's immutable, it cannot do any more order commands, right? Because if row active, you can only issue order commands if you're active. So, and there's no transition, as you'll see, that goes back into active mode. Once you're immutable, you're immutable. And then there's the inherit history. This is where a replica in the next configuration that's still pending can become active. So if you're pending and a quorum of replicas have issued these history statements, then you can go from pending state into active state. And this is how a new configuration becomes active. And it needs so that's the mode, it becomes active. It also needs a history. The history that it uses is it looks at all these history statements from the quorum of replicas that it got, and then it looks for each slot, it looks for the longest proof that it can find in all these statements, and that's what it uses in its own history. Yes? Sorry, when? When does it go into pending mode? So I probably should have a nice state transition diagram. So initially, the replicas in the initial configuration are all active. All the other replicas in all the other configurations start out in pending mode. So they're pending. Now from active mode, you can only go into mutable mode. That's this transition. And from pending mode, you can go into active mode. And so for most, it's a very simple state machine actually. You go from from pending to active to immutable. And that's it, then you're done. The only twist there is that the initial configuration, you start in the active mode. Yes?
There is nothing that can stop a Byzantine replica to go into an immutable mode.
That's right.
Wouldn't it be more difficult to recover from that?
To recover from?
From such a state where a Byzantine replica actually has one when
So Byzantine replica doesn't really have modes, right? So the question is, well, I'm actually not entirely sure what the question is, come to think of it, but I think part of the thing you need to understand is that the Byzantine node can do anything it wants, and it doesn't really have a mode, it doesn't really have a history, it just is, and it does whatever it does. And so thinking of the mode of a Byzantine replica is, I think, not a good idea to start with. So yes, a Byzantine node can pretend that it's immutable and can issue history proofs. It can actually issue a whole bunch of history proofs. Like, a correct replica will not do that. It will only create one history proof. Byzantine node, it cannot create a history proof, or it can create 5 of them. And so, keep that in mind. A Byzantine node doesn't have a mode, but it can pretend to be, it can pretend to be correct to one replica, and then it can say another replica something completely different in order to try and confuse the correct replicas. That's something called equivocation. Okay, so again, we have to map each of these 3 transitions to transitions in this specification, which has just the one apply transition, which adds a slot, a command pair to a history. If we can do that, then we've shown that our implementation is correct. Okay, so let's look at these 3 transitions. We've got the order command. Again, when the last replica on the chain performs the transition, then according to our refinement mapping, we got order statement for all replicas in the chain, and at that point, it's in the history. So that transition of the last replica corresponds to the apply transition in the high-level specification. The order commands of all the other replicas, they don't do anything to the history. And those are called stutters. They just are things that the implementation does in order to do something interesting. Is that clear? We still have to show why that's correct, but I just wanted to show you the refinement steps itself. Okay, so we had 2 other transitions. We got the wedge history one where a process goes from immutable, a correct process goes from immutable into active mode. Well, that doesn't generate any order statements, and it doesn't do anything to the history, and so it's always a stutter. Okay, so once a correct replica in a configuration is immutable, it doesn't issue any more order statements, and so no more commands can be added to the history, at least not by this particular configuration. Right? So once one replica goes into immutable state, in some sense the entire configuration is wedged. And that's why it's called wedge history. Okay, inherit history, again, it doesn't generate any new order statements. It just collects them. There are no new ones that are generated by this particular transition. And so it's also a stutter. It doesn't do anything to the history. However, this is a particularly important one for liveness. It allows a new configuration to get going and make progress. Okay, so does it actually work? Okay, so correct pending replicas. We're going to show that a correct pending replica inherits an order proof for all the commands that have completed. And by that I mean the commands for which the client has received the response. And so why is that? Well, quorums, F+1 or more processes, have at least one correct replica in them. And a pending replica waits for the histories of a quorum of replicas. So it gets at least one history from a correct replica. And since that replica must have issued an order statement for that command, it must be in there. Right? Here's quorums. So there's five replicas in this particular configuration. 3 of them were correct, 2 of them were faulty. Now, the correct replicas will issue correct order statements. let's see. So here are the correct replicas, but now the new configuration doesn't talk to these three, but it happens to talk to those three replicas, two of which are faulty. Yet one of them is correct, and that one will provide a correct order history that the correct replica will use. So because correct replicas have order proofs for all completed commands, and remember the transition is the longest of the order proofs that it can find. Well, what prevents a Byzantine node from creating a very long order proof? There cannot be longer proofs for conflicting commands because it would require the participation of the correct replicas, and so you cannot add things to create a conflicting one without the participation of correct replicas. So conflicting commands cannot get decided. So we get consistency.
It cannot create longer because it has a history of this return just replicate it just after the end.
So in order for it to create a longer, because these chains are ordered, in order to create a longer proof, order proof, it would have to take that one replica that had signed an order statement for a particular command and get it to sign an order statement for a conflicting command, right? Because it needs to build on that. And the correct replica will not do that. Sorry, ordering is... The replicas are ordered within a chain. Right? So there's all kinds of ordering going on in my story. You've got configurations are ordered. Within each configuration, the replicas in the chain are ordered. And on top of that, we're trying to order commands. So, but I was talking about the ordering of replicas. That's true. So it is possible for a Byzantine node to create a longer order proof without, not with the conflicting command, but with the right command. It can create, the Byzantine nodes can extend it with the right command in it. I only said it cannot create longer proofs for conflicting commands, but it can certainly create a longer one for the right command. There's nothing wrong with that. We don't care about that. Again, Byzantine nodes can do anything they want. They can help out. They can do the right thing. Okay, so that's why consistency holds. Now we have to show, does availability hold? Does things eventually complete? So a new configuration has to obtain, in a new configuration, the replicas are pending. So if you have an active configuration, the next configuration, all the replicas sit there being in pending mode. So in order to become active, it needs to hear from a quorum. Well, luckily, there's a quorum in the previous configuration that is correct. And so if there's something wrong with the previous configuration, hopefully so for example, there's no more progress being made, hopefully all the correct nodes will go into immutable mode, issue history statements, and allow the next configuration to become all the correct processes in the next configuration to become active. If you think about it, there is a certain assumption that I'm making here. It's like eventually there has to be some configuration in which all nodes are correct, in which all replicas are correct. Because if there doesn't exist a configuration in which all replicas are correct, then the Byzantine replicas could stop this from working. So that's actually the additional assumption that I'm making, that there is eventually some configuration that has only correct replicas in it, which is a stronger assumption than the Byzantine replication protocols usually make, because there's just a limited number of replicas. Okay, so now so far I've told you, or I assumed there exists an infinite series of configurations. Well, that's a weird assumption to make. I'm going to drop that assumption now. I'm going to make these create these configurations by something called the configuration service. And of course, the configuration service itself has to be tolerant of Byzantine failures as well. So far, so good. And almost there, but not quite. Right, so mostly I just talked about how Byzantine nodes cannot do anything bad. I'm now going to talk about how can the correct nodes ensure that something good will happen, the liveness part. Okay, here's how we do it. Got some replicated object here. We need a configuration service. Well, we're going to replicate it too. And we're going to use chain replication in here, and we're going to use chain replication in there. Now we have one little problem, is that the configuration service also needs a configuration service for this to work. Because I just, did the usual computer science trick. I pushed the problem away one step, a level of indirection or whatever you want. So any guesses on how we're going to fix this problem? That's exactly right. We have the object do the configurations for the configuration service, and the configuration service is going to do the configuration for the replicated object. Sounds good, right? So, so the something is wrong with this replicated object. Some replica is no longer making progress. The other replicas go into immutable state, but now we need a new configuration. This configuration service is going to allocate 3 new replicas, and is going to get the history statements from the correct processes in here, or even from the immutable. It's going to get from a quorum of processes the history statements, gives that to the new replicas, and say, go, you're active now. And vice versa, if something goes wrong here, then its buddy, the replicated object, will do it. Very good question. What if both have, at the same time, some problem? Let's go back to that well, what we do is we just make it a little bigger. Here we got a ring of these replicated objects. And so now we've got 5 objects in a directed ring. And each replicated object does the configuration for the next object in the configuration. And now 5 of these objects have to have simultaneously go something wrong with them. And that is less likely than 2. And so, to make it less likely, we just add more of these objects. And is that, that's kind of a weird thing to do, but we're in I was assuming sort of a cloud environment. We have a data center with billions of objects. And so we organize these billions of objects in a huge ring. The probability that all billion of these objects simultaneously have a failure is very small. But it is an additional assumption that we're making. And that's why we got away with only 2 f+1 replicas instead of 3 f+1. So we are assuming that in each of these configurations, a majority of the processes is correct. And there has to be at least one configuration in which all replicas are correct, because if all of these have a faulty replica in them, we're sunk. So that's what I call the liveness condition. In order for the system to be live, this has to hold. And that's the whole protocol. Okay, let me see how we're doing on time here. How long? I have till 12:30? Okay, so I have 10 minutes. Now, this thing may look a little familiar to you. You've seen one of these things before? Looks a lot like a DHT, right? So we're actually going to build a DHT out of that. So finally, when is he going to talk about DHTs? Here, I'm talking about DHTs. I'm going to skip that. So we need to be able, for DHT, for this thing to be reconfigurable. This thing I'm going to call a band, by the way. An elastic band. And I'm going to call it an elastic band because we have to be able to insert objects to it and remove objects from it. I'm going to show you a little bit about that. So we need to be able to add an object, remove an object. But in the meantime, we also need to maintain an invariant. Basically, forget about what it says there. I'm going to tell it to you in English. 1 second. The invariant is that every object can have at most one configuration service at a time, because if there are two different objects trying to reconfigure the same object, we have a problem. Yes, what was your question?
You mentioned the configurations are different. Why is that needed?
It's not really needed. It's easier to think about it that way, but there's nothing that prevents, if you go from one configuration to the next, you usually want to maintain most of the replicas that were there already. We just add a incarnation number, a view number too. So the replica, it's the same machine, it just gets a new ID. It is a little tricky though in Byzantine. If you have true Byzantine fault tolerance, you don't know which of the replicas were faulty in the previous one, and so you want to have some mechanism by which you can clean up Byzantine replicas. And so we do also want to add to that all the stuff that Miguel talked about yesterday, proactive recovery, cleaning machines. Also, something I didn't talk about today is these checkpoints. These you want to truncate the history. You don't want to just build up an entire. So all that stuff applies here too. I just decided not to talk about it for simplicity. And just I hope that by this I've given you a very simple Byzantine replication protocol that only uses two different kinds of certificates, only uses two F+1 members, and it makes this tiny little additional assumption. That's the basic idea. And now I'm going to show you how we're going to build a DHT out of that. So the invariant, forget about this, the invariant is that every object has at most one configuration object, and clearly in a ring that's always satisfied. But we need to maintain that invariant. So here's our DHT. We need a space, the key space, the address space, so we're going to hash keys onto the range 0 to 1, or if we could think Miguel used 2 to the power 128 or something like that. I use 0 to 1 to make it a little easier, but it's the same kind of idea. I'm going to call each of these objects a segment, and each of these segments is going to be responsible for a range of these keys. So the top one there is responsible for all the keys that hash to 0.9 all the way up to 0, 0 to 0.1. And so each one of these range segments is responsible for a part of the entire key space. And you'll notice that they fit together nicely. Like they're disjoint, but they also cover the entire key space. And we have to maintain this other invariant and that's by the disjointness, that each key can be managed by only one segment. If there's a key in two different segments, it's going to be very hard to have any kind of linearizability on the operations. So we're going to replicate a key only in one of these segments. And it's clearly maintained by this structure. And so we use Byzantine elastic replication in each of these things, and that's the basic idea. If we want to grow this ring because we run out of space in one of these segments, well, what we're going to do is we're going to kind of treat that as a failure. So if we want to grow this, we need to, that particular segment runs out of space. So what we're going to do is we're going to create two new segments. We're going to split the data between them. We treat it as a failure. We're going to wedge it. Correct processes are going to go into this wedge history transition. That stops that entire segment from doing anything. Then we can create two new segments, and we're going to split their range. And then we're going to apply an operation here just by an ordinary command that we're going to set through the chain, which updates that pointer. Voila. We now have a new ring in which we've inserted or split a segment into two segments that now share, split the responsibility. And now we have presumably twice the capacity there. So that's how we can split. I'm not going to go into how you can merge segments, but you can do something very simple, similar. Say again.
The transition to the new
Oh, well, the transition is something that I didn't say too clearly. Each of these objects maintains the configuration of the successor object, right? Because it's a configuration. It maintains two pieces of state. One state is its own state, in this case the key value table. And then there's this other little piece of state, which is the configuration of its successor. So each one maintains the configuration of the successor. Now on the key value table, the operations are put and get and whatever, delete. On the configuration, the operation is update the configuration. So there's an operation that will change the configuration to something else. And it's applied just, it's just an update. It's like a put to a special key, the object that in that segment that maintains the configuration. Yes? Believable? So far, so good. Running out of time, but I think I pretty much covered most of it. I guess I can split that. Okay, so that liveness condition, I guess I can quickly talk about it because it's kind of interesting. The liveness condition was that there cannot be more than F failure in a segment, and at least one of the segments can have no failures in order for this thing always to be able to make progress. So that's a stronger assumption than the usual one where you just say there cannot be more than F failures. It just has one. Now, how can we affect liveness? Well, we can add more segments or we can add more replicas in a segment. So by adding more segments, we'll have more segments, and that is more likely that one of those segments has more than F failures. So that's a bad thing. On the other hand, it's more likely that one of those segments doesn't have any failures. That's a good thing. Now, by adding replicas, we sort of have the opposite. By adding more replicas, it's more likely that there are fewer than F failures. But it's less likely that there is no segment. If every segment had a huge long chain, it gets kind of likely that all of them have a failure in them. So there's this trade-off that we can play with. And in fact, that's what this graph shows. I was talking with Miguel about it, and I happen to have a graph. So what this shows is the number of segments, the probability that the liveness condition holds, and then there's three lines, red, green, and blue. This is for 3 replicas, can tolerate 1 failure. 4 replicas, which can also only tolerate 1 failure, by the way. And then 5 replicas, which can tolerate 2 failures. Right, 2F plus 1, for 2 failures, it's 5. So you can add a replica to one that has only 3. So 2F plus 2 is, 2F plus 2 will still tolerate F failures. So, and here you can see that probability is actually pretty good for 250 segments if you have 5 replicas. It's not so great if you have only 3 replicas. I don't know what it is, but it's somewhere down here. Not good. But you get 5, 6 nines of reliability or something like that, simply by having 4 or 5 replicas with 250 segments. Miguel said, well, I was thinking more about 1 million segments or something like that. In this typical DHT, it's like, this is simulation. I couldn't really do 1 million, but what I can do is analyze this, and I can, for example, show that in order to maintain a particular constant probability of liveness, the number of replicas has to grow logarithmic in the number of segments. So if I square the number of segments, I have to double the number of replicas. So this is 250. If I square 250, I get, 62,000 something. Then I need 10 replicas in order to get that nice line up there. And that's still not 1 million. So we'll add another 2, factor of 250. Now we're 10 million or something like 10 million. That's way more than Miguel wanted. And we need 15 replicas in a chain in order to get those 6 nines of reliability. So if you have 1 million replicas, you probably need something like 12, 13 replicas, I would guess, in order to get a decent reliability. It's just not surprising when you think of it. If you have that many nodes, 1 million of them, and you better have enough replicas in order to get a good good reliability, good durability. Yes.
Is it necessary that all of them have the same number of replicas?
Nope, absolutely not. So you can have different segments of different number of replicas in them. I was, for example, assuming here that all the replicas fail independently. Might not be such a great assumption. If you know something about the failures of replicas, either how likely they're to fail. Like here, I was assuming that all replicas. I forget what the number was actually. Like have some. I think it was. It's actually better remember this. It was a 0.99 reliability per replica. It kind of makes sense when like here, you get 6 nines with 3 replicas. So 2 nines of reliability per replica, and they fail independently. Forgot to say that, kind of important. But if they're dependent, or it's not that number, but if you know something about it, you can calculate for every segment, given a particular set of replicas, how likely it is that that particular segment will fail. And so you can do different chain lengths for different segments, and it's no problem. Okay, so this is pretty much my conclusion slide. So this is something that's relatively easy to implement. It's really not any harder than ordinary chain replication, except that I need to sign some information along the way. It's pretty cheap to run. It uses as many replicas, 2f+1, as PEXIS does per object. And I didn't talk about this, but you can do the same trick that Miguel talks about. You can actually do this with MAX instead of public key crypto. It actually requires a message to go through the chain twice. So rather than going through the chain once and then sending a result, in order to build the HMAC matrix, you have to go through it back and forth. So it does double the number of messages. And it's very easy to add objects, remove objects or segments. So hence the name elastic. Good. So that's, I think, where I'll stop. If there are any more questions, I'll be happy to. Sorry, the lookup will take linear time in terms of the number of segments. Yes. So what I didn't talk about was finger pointers, and I think that's what you picked up on. Question is, the lookup time is linear in the number of segments, which is correct. Oops, I'm not good at this. Somehow I always think that the up button goes back and, or it does go, oh, whatever. Lookup time. There. If I go to any of these segments and I look up, something, a key 0.2 or something like that, well, if it's not here, I have to go to the next one and follow this thing, and yeah, it's linear. However, you can certainly, there's nothing that says that you couldn't, for optimization purposes, add finger pointers, like these long reach pointers, like in pastry. Actually, this is more like chord, but it's just an optimization. For correctness, you can always go along the ring. There's nothing, if you go over here and maybe you go into the wrong one or something, well, if you then start following the ring, you always get to the right key. But with these finger pointer, we can in fact do lookups in order log n hops. Now, I intended this more for, not for the internet and peer-to-peer type of thing, but more as a cloud storage system where they're probably not more than, about 250 segments or something like that. In which case, you can easily imagine that each of these segments actually maintain a total membership. And so there's, in a sense, a finger pointer from every segment to every other segment, and a message can be routed in one hop. But that clearly doesn't scale. Yeah. Sorry,
Your scheme has sacrificed parallelism.
Sacrificed what? Parallelism.
Yeah, compared to Castro's model.
Well, I mean, you can certainly, each of these segments can handle operations in parallel, but the operations within a segment, they're pipelined. So there's still parallelism, right? Operation comes in, so it's dealt with by the head. It forwards it to the next one, and the next one. In the meantime, a new operation comes in. It's handled by the head. So all these replicas, if there's enough load, are going to be busy at the same time. You get full parallelism within a segment because of pipelining. Any other questions? Yes?
So the assumption about the number of failures, does it affect only progress or safety?
It does not affect safety. The assumption about the number of failures only affects progress. Safety cannot be violated. No, wait a minute. Boink, boink. Good question, stupid answer. It can affect, we're in the Byzantine model. I was for a second back in my chain replication paper where it cannot affect safety, but we're in a Byzantine model. If there are more than F Byzantine nodes, they can sign potentially, like if all of them are Byzantine, they can sign any set of order certificates and violate safety. So the bound on F affects both safety and liveness in Byzantine environment. In a non-Byzantine environment, it would only affect liveness. I think it's time for lunch. Thank you.